Hello, welcome back to the class. So, in the last classes you see we have discussed quite a lot about laminar premix flames. Of course, in an engine you encounter turbulent flames, and it can be turbulent premixed, non-premixed or partially premixed flames, but still you understand that the understanding of the laminar structure is very important, because we can consider the unit flamelet to be essentially building up, we can consider a turbulent flame to be essentially an ensemble of these kinds of unit laminar flamelets, where the inside structure may or may not be disturbed depending on the situation. So, to even understand a turbulent flame, it is very important to understand how a laminar flame works, how the different physicochemical processes, how convection, diffusion and reaction are balance each other inside a laminar flame, inside a laminar premix flames. And in that regard we have found out, we have done analysis to essentially find out the laminar flame speed, whereas or the laminar burning flux. Laminar burning flux is essentially the density, unbound density times the laminar flame speed. So, we have found out the planar laminar flame speed using both simple scaling analysis as well as by using a more detailed mathematical analysis called the Seldovich-Frank-Kamenetsky analysis. So, using that we have found out the analytical expression for laminar flame speed. Okay. But of course, you have to recognize that even though it is the laminar flame speed that we have found out, this is very important to even describe the global behavior of turbulent flames, because of the same reason I just discussed, that is, we can consider the full complete turbulent flame to be an ensemble of different laminar flamelets. So, essentially the laminar flame speed equation that we derived, that provides a lot of analysis on what needs to be done to even stabilize turbulent flames, because if locally the flame behaves like a laminar flamelet, that the local velocities have to be of the order of the laminar flame speed to make it stabilized. But of course, if there is something more involved concepts involving like turbulent flame speed, which we will show in due time, that the turbulent flame speed is much bigger than the laminar flame speed, and as a result you can stabilize the turbulent flame statistically, even though you cannot stabilize, even though the flow velocities can be much larger than the laminar flame speed. Okay. So, those things we will discuss later, but now I just want to impress upon you that for a premix flame, laminar or turbulent, the laminar flame speed is the most important quantity. Okay. Even in the expression of turbulent flame speed, you will see that which is the global propagation rate of the flame, whereas laminar flame speed is essentially the local propagation rate of the flame, and what we have dealt with is essentially just a planar laminar flame speed, that is even an idealized laminar flame. So, these things we can connect into different levels with different increasing orders of complexity. So, I just want to impress upon you that the laminar flame speed is a very important quantity, and is a very important quantity in combustion, and especially in premix combustion it is the most important quantity. So, we need to develop tools to understand, we have developed these mathematical tools to describe laminar flame speed, and now we will discuss how this laminar flame speed, which is such an important quantity, can be essentially derived experimentally. Okay. So, here we talk about the different methods. So, we will see here that we will talk about the determination of laminar flame speeds. One can essentially determine the laminar flame speed using this Bunsen flame method, where you have, this is your Bunsen flame, this is the wall, and you have this fuel air mixture coming out through this tube, and this is the flame. Okay. It is essentially a conical flame which is stabilized here. It can be either planar or it can be cylindrical depending on the situation. You can do it both ways actually, and let us consider this is like a planar slot jet, which is in 2 dimension, that is, it is infinite thick on the plane into the board and out of the board. So, it is a 2-dimensional problem. So, we can estimate the global response or the global flame speed by using this thing, that is, if we measure the total mass flow rate coming through this tube, through this tube, if you know that from say your mass flow controller readings or something like that, and you know this density of the unbound mixture, because you know the temperature temperature of that and the pressure of that, and you know the cross sectional area. Okay, if it is a cylindrical tube, you can find out the cross sectional area is just pi r square. If it is a slot jet, then you find out per unit thing actually, or of course you cannot estimate m if it is a fully two dimensional fully infinitely thick tube. So anyways, it's like suppose if it is a j, if it has a thickness like this, if it is a thickness like this, you can find out m, you can find out af, which is the total area like this. Okay, and so you can find out the area given depending on the situation, or if it is just a cylindrical, you find out the area by pi r square, and then using this thing m by rho u af, we can find out that average flame speed. But of course, you see this average flame speed, the flame shape is not same everywhere. For example, here it is more or less like a planar, it's not planar, it's actually cylindrical if you are considering a cylindrical jet, and here it's cylindrical, whereas here there is a concave shape. So then this may not give you correct results. So more refinement would be that, and that is shown here, that if you plot the flames, if you obtain the flame speed versus radial distance, I will show how to do that. It is not same everywhere because the flame structure is different at different places. So on the other hand, you can find out this thing by the following, that if you have a flame like this, and this is the approach velocity, okay, and say the flame is at an angle alpha, give it to the approach velocity, then of course we can resolve this approach velocity which is vertical into two components, tangential component to the component which is tangential to the flame, and a component which is normal to the flame. And then if this is say u0, then of course this one is u0 sine alpha, okay, sine alpha u, so this is alpha u, and this one is u0 cos alpha u. And this tangential component, actually if you just translate it to here, this vector, if you will see that across the flame the tangential component does not change. So that there is pure continuity of tangential component across the flame, whereas the normal component changes because of heat release. Okay, so the normal component will change like this, and the tangential component does not change. So the flame, the actual flow velocity will be deflected like this. Okay, so this will not change, and this will be your basically this normal component will be essentially your u0 sine alpha u times rho u by rho b. That is, it's because this is rho u0 sine alpha u, so this will be u0 sine alpha u times rho u by rho b, because of the fact that your mass has to be conserved. Okay, because across the flame the mass has to be conserved. So and the mass conservation is given by the normal velocity across the surface area. So that is why you get this relationship, whereas this does not change. So you get still u0 sine alpha u, and so that is what causes the deflection of this velocity as you see here. But the most importantly, the fact is that if this flame is stabilized like this, so then it means if you are an observer sitting on the reference frame, sitting on the flame itself, then it means that then it's the flow is approaching to u at a velocity of u0 sine alpha u. Or because the flame is in a stationary state, we can consider then then it is essentially the flame speed, because if this velocity would have been 0, then the flame would have propagated into this unburnt mixture with the same velocity u0 sine alpha u. Okay, so then basically the flame speed we can find out su is equal to u0 sine alpha u. So this is what you get here, that is the local flame speed is given by u0 sine alpha u. Okay, so this is how we can locally calculate the local flame speed of a Bunsen flame. And if you plot this as a radial distance versus flame speed, you will see that this is definitely not, here you see that this is definitely not constant, whereas it remains constant for a certain radial distance, that is up to this region, whereas very near the rim, at very near the rim, which is at large radial distance, you have heat loss into the walls, so that is what the flame speed reduces, whereas here the flame speed can change because of the additional curvature effects, which we will later call as stretch effects. Okay, so because of this the flame speed changes, but this at the if you estimate this from a photograph of the Bunsen flame, you can if just by estimating the flame angle and by knowing the mean flow velocity u0, which of course has to be uniform at this state, otherwise this flame will not be like this, it will be a different kind of shape. That is, if you see that this flow velocity is is uniformly going into this, then it means that which is given by u0. So then it means that the flame speed is given by u0 sin alpha u. You should do this on your own to convince this why it is so. So flame speed is the definition of flame speed is the speed at which the speed of the flame relative to the local fluid velocity. So if the fluid velocity is a speed or the definition of the local flame speed is the propagation rate of the flame with respect to the local fluid velocity. So if the local fluid velocity is at rest, of course the flame propagates into the unbound fuel air mixture at a velocity which is equal to the flame speed. On the other hand, if the fluid velocity is on the other hand, if the flame is at rest, it means that the fluid velocity must be fed to the flame at a speed equal to the flame speed, so that to ensure that the flame is stationary. Okay. So this is how you estimate the flame speed, and of course there are other methods. There is this porous plug burner method. So we can have a porous plug to just stabilize the flame a little bit upstream, and then of course it has some heat loss. So you can do many things just to minimize the heat loss, and I will not talk in these details, but this is just another method by which you can estimate the flame speed. But this is interesting, this 1D spherical and cylindrical flame. So basically you fill up a spherical vessel with a fuel air mixture and fuel plus air mixture, and you ignite at the center with a pair of electrodes. Okay, and this flame essentially grows like this. Okay, so with time it grows like this, and of course by estimating the radius one can find out the radius versus time, and then differentiating with respect to time, finding drf dt, one can find out the local correlate the local flame speed. Of course the indirect way is that one can estimate the pressure rise in the chamber and relate it to the propagation which generates the hot product causing the pressure rise. But better is you directly image the flame front with a high speed camera, and then you measure the quantity in the downstream value and then convert. Okay, so SU0 is basically is rho B0 times rho B0 is essentially the adiabatic burn gas density divided by rho U0 times SB0, and then you write that you can show that is this SB0 is essentially will be equal to DRF dt, and but of course there is a flame stretch which we will discuss later, that is the surface of the flame is not planar, it is stretched because of the curvature effects, and using that we need to essentially subtract the flame speed, the flame stretch, to arrive at the planar laminar flame speed, which is basically the signature value for the given fuel air mixture at a given temperature and pressure, upstream temperature and pressure. So here also the other methods is that you find out one can do a stagnation flame method. Of course the flame is stretched here as well. So in the stagnation flame method, what we have is that you have two jets like this, both are like fuel air mixture, which are like impinging on each other. This jet comes like this and this jet comes like this, and they impinge on a stagnation plane, and the flame is formed in this in the little upstream and downstream ahead of the stagnation flame respectively, as you see here. So here is this jet, diverging jet, and of course you see that because of the divergence there is a stretch, the flame is stretched, and we have to essentially subtract the flame stretch out to get the planar laminar flame speed, which is the parameter of choice. Actually the planar laminar flame speed, because it, as you see, it involves both transport as well as reactions, is a very good choice for validating detailed reaction mechanisms. So that is also one of the reasons why the people have spent a lot of effort in estimating the flame speed or the planar laminar flame speed at by different kind of methods with different orders of with different and try to improve the accuracy of these different methods by which flame speed could be estimated over time. And nowadays people either use this spherical flame method or this stretch flame method, the stretch flame or this counterflow flames to estimate the planar laminar flame speed. So as I was saying that yes, the results can be it is used for validating the reaction mechanisms and for transport properties, especially the radicals. So now next question is that so if flame speed is such an important quantity, which if flame speed is really such an important quantity, which characterizes the flame, both the propagation behavior of the flame and also and that comes out because of certain unique structure of the flame unique structure of the diffusion region, of the reaction region, then what does this really depend on? And of course it's a practical interest, because you fill up a tube with a premixed fuel air mixture and you ignite at the end, okay. And of course the speed, the flame will propagate from one end to another end, and it's a practical interest to know what would that speed be, because of course as we discussed later previously, that in a premixed gas turbine combustor, locally the flame will be stabilized only at that point where the local flame speed is equal to the local normal flow velocity. So it is in designing combustors also, if you are designing a nearly premixed combustor, one must have a very clear knowledge about what the flame speed of the mixture you are working with, otherwise you cannot stabilize the flame, okay. So flame speed is really important in that respect, and we need to really understand what does the flame speed depend on. So if you remember, the flame speed we discussed was obtained like this, that is the Zeldovich-Frank-Kaminsky analysis gave me the flame speed to be like f0 square is equal to lambda by Cp times Bc times Lewis number times e to the power of minus Ta tilde by Tb tilde. This was your minus activation energy activation temperature by the burn gas temperature, and this was equal to the minus of Arrhenius number and followed by this Zeldovich number squared, okay. So now Zeldovich number, if you remember, Zeldovich number involves this thing, that is Ta tilde, if you write in tilde terms, that is Tb0 squared tilde, and this was Tb tilde minus Ta tilde, which is equal to 1, okay. So if you remember that, okay, now Ta tilde, if we consider it as constant, you say Zeldovich number is essentially proportional to Tb0 square. So if you see that, you can write this as this f0 square is essentially your Tb0 tilde to the power of 4 because of the Zeldovich number square, keeping the T activation energy constant, times Ta tilde by Tb0 tilde, okay. So you see that to the leading order, and of course we can write this for any mixture actually, f0 square f square later, that is any burn gas burnt laminar burning flux is essentially is equal to Tb tilde, which can be any burn gas temperature, need not be adiabatic also, minus Ta tilde by Tb tilde, okay. So you see, the fact of the matter is that the F0, that is the burning flux, has a very strong dependence on temperature, okay. So this thing, that is the burning flux having a very strong dependence on temperature, is actually shows up in the experiments or in the simulations also, which tells that and we expect that the burning flux will have a very strong temperature, or the adiabatic flame temperature, or the burn gas flame temperature dependence. And yes, we find that in experiments, that is if you see that, we see that the burning flux to the leading order, or the laminar flame speed to the leading order, is actually governed most strongly by the adiabatic flame temperature, okay. And this is a testimony to that fact, that if we plot laminar flame speed on the y-axis and the equivalence ratio on the x-axis for a methane air mixture, and this adiabatic flame temperature on the other y-axis, if this is your adiabatic flame temperature, okay, you see that this is your essentially your flame speed plot. So the flame speed mimics almost the adiabatic flame temperature. Of course it can shift slightly on the right hand side and left hand side, because it has got other dependence through Lewis number, etc., okay. Now that is also has a very important effect in this thing. So you see that if you consider this, all these alkanes, like all the way from methane, propane, ethane, propane to butane, pentane, hexane and heptane, okay, you see that the flame speed, the laminar flame speed of methane is smallest at a given equivalence ratio, then it increases to some extent for ethane, and then it increases slightly for propane. And then when we go here, you see that all these laminar flame speeds of butane, pentane, hexane, heptane are all same. Why is the reason? reason? The reason is actually the adiabatic flame temperature. You see, you go to this plot and you plot adiabatic flame temperature. You see that yes, the methane has the lowest adiabatic flame temperature, which is correct, and but then ethane increases slightly, and then this adiabatic flame temperature does not increase at all from propane, butane, pentane, hexane, and heptane. Okay, at a given equivalence ratio, very small, it changes. So that is why this flame speed also, because the flame speed to the leading order depends on adiabatic flame temperature, it does not change at all for the it does not change at all between butane to heptane, and this is called the fuel similarity. So butane to N heptane, the flame speed does not changes, and the reason is purely the fact that your adiabatic flame temperature also does not change. Okay, and what happens with hydrogen? With hydrogen, it is a little bit little tricky, but though the behavior holds more or less. You see that here, if you plot the laminar flame speed on this axis, y1 axis, and the adiabatic flame temperature on the y2 axis as a function of equivalence ratio, this is your adiabatic flame temperature. Okay, but this is your laminar flame speed. So yes, it changes, it has a bearing to that. But you see here, this Frank-Kamenetsky analysis also says that the F0 square will be proportional to Lewis number. Okay, and this effect is really exaggerated for hydrogen, because hydrogen is a very small molecule, so its diffusivity is very large. Okay, so which is why in the lean side this Lewis number is very small, its molecular diffusivity is large, and on the richer side, that is where the effective Lewis number is obtained by that of oxygen. So this Lewis number is 2.3. So because of this strong change in Lewis number, this F0 square shows a little bit deviated behavior from this adiabatic flame temperature. Okay, and this you will see that later these effects are most significant for essentially the stretch flames. So this shifting of the flame speed, the flame speed will actually have a strong impact on the stretch rates, and that will be controlled by this Lewis number, that we will see later. Okay, for now we will just focus on the planar laminar flame speed, because then that is why we have this F0. Okay, so the planar laminar flame speed, once again you will see that the dependence on the molecular structure. How does it depend on the molecules? So we see that if you plot with like from C2H6, that is ethane to ethylene to acetylene. Okay, so you see it increases at 1 atmosphere, but is it increasing due to the adiabatic flame temperature? Because your acetylene adiabatic flame temperature is large. So what we can do is that we can choose the oxidizers in such a way, or we can dilute the oxygen with such an inert in such a way, so that the adiabatic flame temperature is constant at different cases, and then also we see that the acetylene wins over ethylene and ethane. Okay, so so it is acetylene despite. So here the fuel structure also has some effect through on the flame speed, and that cannot be solely captured by adiabatic flame temperature. So yes, indeed adiabatic flame temperature is very important, but it is not the only factor that controls the flame speed behavior. So that is what is the lesson of this thing. Okay, so one very important thing is the dependence on pressure. Why? Because you see engines operate at a high pressure, both car engines as well as the gas turbine engines. Say gas turbine engines operate at a pressure of 30 atmosphere, 30 or 40 atmosphere, right? So we need to know, only knowing how the flame behaves in 1 atmosphere is not good enough. So we need to know how the flame behaves at 30 or 40 atmosphere or 50 atmosphere. So what we see is that if you remember that we obtained this in previous classes, we obtained this relationship that how much does F0 on what should F0 depend on? Yeah, this is the thing. So it was shown that that F0 is going to increase with pressure P to the power of n by 2 when n is the order of the reaction, whereas S, which is F0, that is a burning flux normalized by density, that should behave in a manner P to the power n by 2 minus 1. So depending on the order of reaction, of course F0 must always increase with pressure irrespective of the order of the reaction, because the burning flux must increase with pressure, and that comes from the fact that the whole reaction rate is increasing at high pressure because collision is higher. But with S, because the density also decreases, this is not guaranteed. So depending on the order, the pressure can actually, the S actually can increase or decrease with pressure. Okay, so here we will see what is happening for actual fuels. So you see that with pressure, as we have seen that the dependence on pressure comes on the flame speed through two things, that is it comes to chemistry, it comes to density. Okay. The chemistry part is in the, when you say F0 is essentially this burning flux is proportional to W reaction rate to the power of half. Okay. And then the reaction rate we can correlate with pressure. Okay. So, but then as SU, there is a flame speed that also contains your density. So, the density is the density effect is essentially comes the density effect is also can take away some of the chemistry effects on the when it comes to dependence on pressure. So, we see that that S here, if you consider hydrogen air flames at different equivalence ratios, we and at different pressure, we see that this highest is for 1 atmosphere and then it reduces with the increasing pressure. So, the flame speed essentially reduces with pressure, and the reason is because the density is actually reducing. Okay. So, the density is actually increasing with pressure. So, as the density increases, you have more gas to heat up. Okay. So, and that is why the flame speed is retarded at high pressure. So, it is an effect of density, it is not a chemistry, whereas if we really want to understand how the flame speed depends on pressure, the better quantity to look at is this burning flux, which is F0 is equal to rho u times SU 0. Okay. So, this quantity, because it accounts for the density weighted flame speed, essentially density weighted flame speed. So, F0 is a proper parameter because it is only affected by chemistry and not affected by density. Okay. So, we find that this if we consider the same thing and if we plot the laminar burning flux with equivalence ratio, we see that with the increasing pressure, the laminar burning flux at a given equivalence ratio monotonically increases, and that is the pure effect of chemistry which we have just discussed. So, as we said that F0 usually increases with increasing pressure and flame speed actually decreases with increasing pressure. So, that is one important thing we have to keep in mind. Okay. So, now using that we can using just the relationship that we wrote, we can find out the global order of the reaction, and we see that the global order of the hydrogen air reaction, of course, as you have seen that hydrogen air combustion involves at least 9 species and 19 or 20 or 19 reactions, and those whole thing can be just simplified into one reaction order using this burning flux and the pressure dependence. So, if we plot that, we see that this is how for different equivalence ratios the global order depend on. It starts from somewhere near 2 for larger equivalence ratio cases, and then it drops and then it can again increase. So, that is why, because it is less than 2, it is actually mostly it is less than 2, we have basically the flame speed decreasing with pressure. We can find out the overall activation energy, also the global activation energy for the whole hydrogen air reaction using this formula as well. Okay. So, this results demonstrate that the role of the pressure on the 2 body reaction and the 3 body reaction, and it is not possible with n less than 0 also. Okay. So, because the role of 2 body branching reaction is the role of pressure of the, we see that the 2 body branching reactions are promoted with pressure and the 3 body branching reactions terminations, the reactions are not promoted as such, the flames behavior is promoted or retarded with pressure, and this is not possible with N0. But of course, this is a fact on the burning flux, whereas the actual behavior comes from the fact that, of course, reaction rate increases with pressure, which causes the increase in the burning flux, whereas the flame speed reduces with pressure, and that is a purely an effect of density and is not an effect of reactions. So, the fact that another parameter that has been left is essentially this transfer properties. Okay, we have talked about adiabatic flame temperature, we have talked about molecular structure, we have talked about pressure, we have not talked about transfer properties. So, but as you see that your F0 square has proportional to lambda by Cp when all of the parameters are constant. So, how the transfer property affects the flame speed can be easily found out by experiments where the nitrogen can be replaced with argon, and because they have similar molecular weights and diffusivities but different Cp, the flame temperature, the adiabatic flame temperature is actually changed. And okay. So, flame speed, we just manipulate flame speed using this property. We can manipulate flame speed with different inert substitution. As you see that because the CPs are changing with different inerts, though their diffusivities are similar, at least for nitrogen and argon. With the nitrogen and argon, as the CP is changing, your flame speed is actually increasing with argon air, and it increases further with helium air, because you have a less if the CP is less, you have less energy to be spent to heat that gas up, right. So, the flame speed essentially is higher to in these cases. Okay. So, this is CH4 in various parts. This is of course considers to be the equivalence ratio, but will to be equal to 1 behavior here we get. So, similarly with CH4 in different CH4 percentage in different years, we see that this is the laminar flame speed, and this is the burning flux, and of course the density also plays a role. So, but still the nitrogen air has the least burning flux, followed by helium air, because helium is very light, and then it increases up to argon air. So, this is what we get.